This conference will now be recorded.
Very good evening, students. Today we are continuing with electromagnetic induction part. Here we will be concluding this part today with the discussion of few more interesting problem from previous JEE paper, and then we'll move on to alternating current part along with some induction problem combined with that. So today let us start our discussion. So this is the first question which we are going to discuss. So this question says that a conducting bar of length L is free to slide on two parallel conducting rails. You can see that these are two parallel conducting rails and this is another conducting bar which can move or slide over this conducting rails. Two resistors R1 and R2 are connected across the ends of the rails. There is a uniform magnetic field B pointing into the page. An external agent pulls the bar to the left at a constant speed V. An external agent pulls the bar to the left at a constant speed V. The correct statement about the direction of induced current I1 and I2 flowing through R1 and R2 respectively is I1 is in clockwise direction, first option, and I2 is in the anti-clockwise direction. Second option says both I1 and I2 are in the clockwise direction. C says I1 is in anti-clockwise direction and I2 is in the clockwise direction. And the option D says both I1 and I2 are in the anti-clockwise direction. So as you see the figure, this is a problem from motional EMF. Motional EMF. As the rails, as the conducting bar moves over this or slides over the conducting rail, there will be change in the flux. As you see, if you can see this, like if you can imagine this particular resonant is on the plane of the paper and the magnetic field is then entering into the plane of the paper perpendicular to it. So, and there are two resistors R1 and R2 connected across the rails. So there are two currents. It is said that there are two currents. I1 is through R1 and I2 is flowing through R2. So when this conducting bar moves towards left, then what will be the direction of the current in the resistance R1 and what will be the direction of the current in the resistor R2? So as you know from Lenz's law, what Lenz's law says, induced EMF will be such that it opposes the cause. Okay, opposes the cause. That means, look here, the change in the flux, how the change in the flux happens in this case. See here, as you move this conducting bar, how the flux changes. Flux means B into A. Okay, since these are perpendicular to each other, so B dot A. So B dot A is the total flux. Okay, and A, how A changes. Actually, if you see motional EMF, it will be BVL. Okay, BVL. Okay, as the area changes, like like you have L into dx dt. So that's how the area changes. Here, because of the change in area, as the conducting bar moves, we get motional EMF. So when it was in the middle, see both side, actually the area was area of this left part. Suppose this is one portion 1 or region 1, and this is region 2. So when this was at the middle in the beginning, then both side area seems to be equal. But when the bar is moving, or it is moved somewhere here, suppose it is here now, look what is happening. The area in this, like region 1, area is actually getting reduced. Area gets reduced. So when the area gets reduced, phi also will change. So phi is actually decreasing, the flux decreases. Okay, if the flux decreases, the induced EMF or the current will be in such a direction that it can oppose the change in the flux. That means, see, in this loop now, in this loop, this particular loop 1, here the direction of the current will be such that it will, see, since it is getting reduced, so magnetic field has to be added up. Okay, so the induced field should actually get added up with the existing one, such that the flux will be, the decrease in flux will be opposed. I hope you are understanding. See, if you apply the right hand rule, okay, right hand rule, so the magnetic field induced current should produce a field which is also getting into the plane of the paper. Okay, because the flux is reducing as this bar goes onto the left hand side, so the area gets reduced. Since the area gets reduced, the flux reduced. If the flux is reduced, then EMF will be changing in such a way that, or the induced EMF will be such that it will flow a current which will oppose the change or reduction in the flux. So in this case, my way of thinking is that if the induced magnetic field by the induced current is in the same direction as the field existing in this region, then only that can be opposed. Okay, the reduction of the flux can be opposed. So that's why, see, in this region, if the current is flowing in this way, okay, then it is possible that the induced magnetic field will be along the same direction as the existing one. At the same time, look in the region 2, see, excuse me, in the region 2, the area of this loop 2 is actually increasing. Hence, flux linked in this also increases, phi increases. Okay. Therefore, the EMF will be in such a direction that it will flow a current such that the increase in flux will be obstructed. That means the direction of the current will be such that, induced current will be such that it will produce a magnetic field exactly opposite to the existing one. So in this case, it should be B minus B induced such that the total flux change, excuse me, flux change due to increase in area will be obstructed. So if it is, see, if the current is flowing in this direction, so then only, so this in this direction, then only it is possible. Excuse me. So I mean to say that the current in the R2 has to be in the anticlockwise direction. So this is B induced. This is B induced. And the current in the R1 has to be in the clockwise direction. So we'll see, sorry, yeah, so clockwise direction. So I1 has to be in the clockwise direction, I2 has to be in the anti-clockwise direction. So the first option will be the correct answer for this case. Okay. So you have to keep in mind this Lenz's law. An induced EMF will flow a current in such a way that the induced magnetic field will either oppose or adds up depending on the situation, whether the flux increases or decreases. Okay. All right. We'll go to the next. So the second problem says that a conducting circular loop is placed in the xy plane. Let us say this is the xy, let us say this is xy plane. So this is x, this is y, xy plane. So what is the area, like normal to, or the area vector for this loop? This will be outward normal, which is in the z direction. If this is z, so this is the area normal. Okay, area normal in the k-cap direction. So there is a conducting circular loop placed in the xy plane. You can see that, and the magnetic field B is given. Magnetic field is 3t cube j cap plus 3t square k cap. That means it is in the yz direction. Okay, z and y. So yz direction, sorry, yz plane, in the yz plane. So the radius of the loop is given, that is 1 meter, radius of the loop. The induced EMF in the loop in time 2 seconds is, so induced EMF is given in time 2 seconds, it is given as n pi v. Then you have to find out the value of n. Okay, so this is the question. So we know induced EMF can be obtained by getting minus d phi by dt. So this is the thing. So we have to find out first what is phi, and then we have to take time derivative of that. Okay. Excuse me. So what is phi? Phi is B dot A. I have already shown you what is the direction of A and what is the magnitude of the area. So this is actually pi, and radius is 1 meter, so 1 square k cap. So we can write B is 3t cube j cap plus 3t square k cap dot pi k cap. Okay. So this is the flask. Let me take the dot product. So jk will be actually perpendicular to each other. So you'll get actually 3 pi t square. This will be the flux. 3 pi t square. Okay. Now let look what will be the induced EMF. So that will be d phi by dt, d phi by dt, or ddt of 3 pi and t square. So this will be 6 pi t. Okay, 6 pi t if I take the derivative. And what is the induced EMF? In 2 seconds, it is asked at 2 seconds. Then, therefore, induced EMF at 2 is equal to, sorry, t is equal to 2 seconds is minus 6 pi into 2. This is the volt. Okay. So there it is given n pi volt. So here we get minus 12 pi volt. Okay. So let us take the magnitude of that. Let us don't worry about the minus sign here. So then n pi. So this n pi can be equated to 12 pi. So what is the value of n then? N is equal to 12. So this is the answer. So option C will be the correct answer here. Now let us solve the third problem. The third problem states that so a solid metal cube of age 2 centimeter is moving in a positive y direction at a constant speed 6 meter per second. A solid metal cube. Let us try to draw a metal cube. So let us imagine this is x-axis, this is y-axis, and this is z-axis. Okay. So metal cube of age 2 centimeter, each of them are. So let us say A is the like A is the side. So 2 centimeter is moving in the positive y direction. So this is moving positive y direction. So there is a uniform magnetic field in the z direction. So you look, these are two perpendicular directions. Z direction, the magnetic field is in the along the Y direction, the cube is moving. So if you look V cross B, so V is along J cap direction and B is along K cap. So J cross K will give you I cap. So you can see that the charges or the ions will be actually getting deflected. Positive ions will get deflected along this, like in this space. So positive charge entities will be here at this edge, and negative charge entities will be here in this edge. Okay, that means there will be a potential difference between the two faces of the cube perpendicular to the x-axis. Okay, so these two faces will actually, if you just bring a voltmeter, you can see there will be induced EMF across this, like between two faces which are perpendicular to the x-axis. You can see that. So you have to find out the value of the induced EMF. So this, this cube is actually moving. Cube has side A 2 centimeter. 2 centimeter means 2 into 10 to the power minus 2 meter. 2 into 10 to the power minus 2 meter. So in this case, B is given as 0.1 Tesla, and the speed of the cube with which it is moving along the x direction is 6 meter per second. So we'll be actually using BVL. Instead of writing L, we'll be writing A, which is the dimension of the cube, edge of the cube, one of the edge of the cube. Okay, along the y direction. Okay, so BVL. So L is replaced by A here. BVA. So B is 0.1 Tesla, B is 6 meter per second, and BVL, L or A, so that is 2 into 10 to the power minus 2. Okay, and this will give you, this is EMF, so EMF will be in volt. So we get 12 into 10 to the power minus 3 volt. So which is 12 millivolt. Okay, so this is the answer in this case. Okay. Now we'll move on to the next problem. So in this problem, there are two identical excuse me, not identical. There are two coils P and Q. They are separated. Suppose this is one coil. Sorry, this is one coil. This is another coil. Okay, so they are separated by certain distance. Suppose D or L, whatever it is. When a current, and this is suppose P, this is P, and this is Q. When a current 3 ampere flows through P. Okay, let us say current 3 ampere IP. 3 ampere is flowing through this P, then a flask will be linked with this Q. This flask, let us name this flask Q, phi Q, produced by, produced because of the current in the P. So we name the flux link with the Q as phi QP. That means phi, or the flux linked with the Q coil due to the current flowing in the P. Okay, and that time no current flowing or passed through the Q coil. When no current passed through P and a current 2 ampere passes through Q, what is the flux link in this P? That means you have to actually calculate the flux link with the P. That means phi PQ, you have to find out when the current flowing in this Q coil is 2 ampere. Okay, so this is the question. So you have to find out the flux link in the PQ, sorry, flux link in the P coil when the current 2 ampere is passed through the coil Q. Okay, so this is the question. So you can guess that this problem is from mutual induction. Mutual induction. It is problem from mutual induction. And you know, if you have two coils like this, when they are coupled by mutual induction, their coupling constant or their mutual inductance in each will be the same. I can say mutual inductance for P and mutual inductance for Q will be the same because they are connected through the same uh, coefficient. Okay, and you know this phi. See, mutual inductance. What is the definition of mutual or self inductance? Phi. Flux is the mutual coefficient of mutual inductance into the current. So if I write phi, that is in Q, it is produced by, so then it, you know, like it has to be Q, MQ, and current flowing in the P. So this is how we can write. Phi is equal to Li or Mi. So I has to be flowing through the other coil when you are calculating the magnetic induction or magnetic flux in some other coil. Okay, so I'm calculating flux link with this Q when the current IP is flowing through the coil P, and that's why I have taken this mutual inductance MQ. So from here I can write actually MQ is equal to phi QP divided by I. Similarly, I can write to Q I Q. Okay, now this is one equation and this is another equation. I can just take the ratio of these equations. Okay, since this MP and MQ, they are equal to each other, so look what I can do. P and M, they are equal. So MQ by MP is equal to phi QP divided by IP, and MP again it is phi PQ, and in the numerator it will be IQ. Okay, so I'll just erase this part. This also not required. We have understood the problem. Now we are just calculating. See, from here what we have to find out actually phi pq. Phi pq we have to find out. So phi pq is equal to mp by mq into, see here, phi pq we have to find out. So mp by mq, and here it was phi qp divided by ip into iq. Okay. So from here, see, mp by mq, they are equal to each other, they will get cancelled. And see, phi qp is already given, that is 10 to the power minus 3 Weber, and this has current. So iq is given as 2, ip is given as 3, so 2 by 3 into 10 to the power minus 3 Weber, that means 6.67 into 10 to the power minus 3, no, minus 4 it will be, okay, minus 4 Weber, okay, 6.67. So option B will be the correct answer in this case. So this is a problem of inductance, mutual induction. Okay, I hope you have understood this. We'll move on to the fifth problem. So this problem you can see here. The problem says that the variation of induced EMF with time in a coil, if a short bar magnet is moved along its axis with a constant velocity, is best represented as. So what is the question? The question is variation of induced EMF. Okay, so variation of induced EMF with time in a coil if a short bar magnet is moved along its axis with constant velocity is represented. See, I'll tell you what is the problem. The problem is here. See, you have loop like this, coil like this. Okay, now you have a bar magnet, short bar magnet it seems, and you are just moving this bar magnet through this. Okay, you are moving through this. So when your bar magnet, suppose this is south pole, this is north pole, whatever it is, when it is, it has just entered, there is a flux link in that, okay, in the loop, and there will, since it is moving, there will be change in the flux, so there will be induced EMF. And you look, the direction of the induced EMF while entering and induced EMF direction or polarity of the induced EMF while leaving will be different. So direction of the EMF will be different when it is leaving the coil than when it was entering. That means, you know, in the induced EMF there will be obviously a polarity change with respect to time. There will be a change in the polarity. So look, if I say it was earlier, it's 0, then negative, then it goes to 0 again, and then positive. So this can be a situation here because the direction of the induced EMF will be different while entering and leaving. So among these four options, you look, there are no negative sign or no polarity change. So there are polarity intact here, here, here. They have kept their polarity intact. Okay, polarity intact. So they don't have change in the polarity at least. So only this option is there where there is a change in the polarity. Therefore, option B will be the correct answer. Okay. So option B, which shows that there is a change in the polarity, that will be actually the answer for this question. So with this, we have more or less covered many problems in induction part. Now I'll pick up one or two problems from AC alternating current. Obviously, here also there will be the concept of induced EMF, so I can write here in the title part electromagnetic induction and AC current. Okay, alternating current. Here there will be LCR circuit, LR, CR, and LCR circuits. Okay. So let me first take up one simple problem. This is actually from the mains. Let us say this is the sixth problem for today. It is from paper 2010 JEE mains. An AC voltage source, an AC voltage source an AC voltage source of variable angular frequency of variable angular frequency omega and fixed amplitude fixed amplitude V0 is connected in series with capacitor. Is connected connected in series connected in series with a capacitor of capacitance C capacitance C and electric bulb of resistor and an electric bulb electric bulb of resistance capital R. An inductance 0 has been taken when omega is increased. Then what are the lower options, like options below? What is the option, like which option will be the correct answer for this case? The bulb glows dimmer. Then second option, the bulb glows brighter. The bulb glows brighter. Option 3, total impedance of the circuit unchanged. That means I'm writing as this of circuit. Option 4, total impedance of the circuit increases. That means Z increases. Okay, so these are the options. You have to answer for this question. So AC source, I'll just draw it, an AC source, okay, which is connected to a capacitor through a resistor in series. Okay, in such case, so this is C. So in such case, okay, there is another one. Along with this resistor, there was a battery also. Sorry, bulb also. Let me draw it bulb here. So there is a bulb. So the question is whether it will be glowing brighter or dimmer, or the circuit like Z impedance, total impedance of the circuit changes, or total impedance of the circuit Z increases. That means total angular momentum increases. So what is the answer in this case? So when current excuse me, just a minute. We have to find out what is the answer for this problem. So in this case, see, if I talk about the impedance in case of CR circuit, what is impedance? C and R in series. What will be the impedance? Total impedance will be square root of R square plus xc square. Xc means 1 over omega. 1 over omega square. Okay. Now, omega is actually time varying, it says. So when omega increases, here x is omega increases, then xc will be decreases because x is a constant quantity. Okay. So variable frequency for both that will be the same. As omega increase, c will be xc will be increase decreases will be decreased. Okay, so xc will be decreasing or z will be decreasing. Hence, the power increases. Therefore, here actually, since omega increases means xc decreases actually. Okay, as you see from here, if omega varying actually, it said when this increases, then xc decreases. Therefore, the bulb will actually glow brighter. Bulb will actually glow brighter because this the total impedance decreases. Okay, so bulb will glow brighter. That's the answer. This is what brighter. So the question was actually amplitude doesn't change, but angular frequency changes. Such an AC source has been borrowed. So we have seen XC like this. Okay. So in this case, Z of the circuit increases. Sorry, decreases. Okay. So we'll conclude our class today here. In the next class, we will solve many other problems on alternating current. So the answer for the last question is that this also is true, and this bulb will glow brighter. That is also true. Okay. So sorry, Z will not increase. That will actually decrease. That will change. In fact, that will change. That is sure. So the second option will be the actually most appropriate answer. Let us go with that. And we'll stop it here for today. Next day we'll take up with new problems. and interesting problems on AC or alternating current chapter. Okay, so thanks for your patience.